Good afternoon, class. Here's the third part of 3.5, the chain rule called related rates. And we covered just about everything, including the chain rule. We looked at implicit differentiation and now related rates. Reminding you of differentiation formulas, of course, starting with the definition. dy dx is limit of delta y where delta x as delta x approaches 0, or f prime of x is limit of f of x plus h minus f of x over h as h approaches 0. Then we have various theorems. For example, the power rule, trigonometric functions. For example, the derivative of x to the power n is n x to the power n minus 1. The derivative of sine is cosine. The derivative of cosine is negative sine, and so on. The product rule, the quotient rule, composite function resulting in the chain rule, and exponential rules where every derivative starts with the function itself, and then we add something according to the chain rule or the logarithmic properties. Now, 3.5 part 3, related rates. If we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume than the rate of increase of the radius. In a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another one, which may be more easily measured. So here's a procedure. Number one, find an equation that relates the two quantities. Number two, use the chain rule to differentiate both sides with respect to what? Time, which means t is the independent variable. So dy dt is dy du du dt. That's the idea behind related rates. For example, as a warm-up example, air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Let's see what's given, what's missing. Let's discuss that, and then we go with the symbolic format. So what is given? The volume is increasing at 100 cubic centimeters per second. So the rate of increase of the volume of air is 100 cubic centimeters per second. What are we looking for? The rate of increase of the radius when the diameter is 50 centimeters. So what is the shape? Here's a spherical shape where the volume is 4/3 pi r cubed. From the center to the sphere is called the radius. If you go both sides, is the diameter, and the relationship is that d equals 2 times r. So we need the volume. We should know that. And now we're going to write this symbolically. This means dv dt is 100 cubic centimeters per second. And this means we want dr dt when d is 50 and r is half of that, 25 centimeters. This is explaining the question in a symbolic format. So we start with v equals 4/3 power cubed. We want to find dv dt. And from v to t, the intermediate variable is r, which means dv dr dt. That's what we are looking for. Meaning we are going to differentiate this with respect to r and then tag along dr dt. So having said that, notice this is a coefficient, this is a number, this is a multiplier. So dv dt starts with 4/3 pi. Then we are looking at r cubed, 3r squared times dr dt. It's 4 pi r squared dr dt. Divide both sides by 4 pi r squared. So dr dt becomes dv dt over 4 pi r squared. We're going to plug in. dv dt is 100. R is 25. The product of 4 and 25 is 100. We get 1 over 25 pi precisely. And so we write the radius of the balloon is increasing. Why is it increasing? This is positive. At the rate of precisely 1 over 25 pi, or roughly 0.0127 units of the radius over units of time, centimeters per second. We should answer it with the proper units, and the units, just you look at the formula, you should be able to come up with the answer. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at the rate of 3/2 feet per second. Find the rate at which the area of a circle is changing when the radius is 4 feet. So what are we dealing with? We are dealing with a circle. What do we know about the circle? From the center to the circle, this distance is called the radius. If you go both sides, is the diameter. D equals to r. Circumference is 2 pi r. Area is pi r squared. We need the area equals pi r squared. We don't need the rest of them, but I wanted to remind you all of those that you're supposed to know. And so what are we looking for? A equals pi r squared. What is given? Radius is increasing, so that means dr dt at this rate. Dr dt is 3/2 feet per second. What are we looking for? dA dt at what point? When the radius is 4 feet. Very straightforward, everybody. So if A is pi r squared, we are looking for dA dt. What is dA dt? Pi remains because it's a multiplier, is a coefficient. You just work with r squared, you get 2r dr dt, which means 2 pi r dr dt. That's the meaning of it, of course. So replace the r with 4 feet, dr dt with 3/2 feet per second. And we end up with 12 pi precisely units of area, square feet, per units of time, second. So 12 pi square feet per second. This is a rough estimate. Always go with exact. So let me just write that. This is an exact answer, everybody. Always go with exact, okay? And then if they ask you for decimals, then you follow that. 37.6991 square feet per second. Again, this number is positive. What does that mean? The radius of the balloon is increasing at a rate of 1 over 25 pi, roughly 0.0127 square feet per second. The area, everybody. I mean the area. Find dy dt for the equation 4x plus 3y to the power 4 equals x squared, where dx dt is 10, x is 4, y is negative 2. What is important to understand, the moment you see dy dt, that means t is the independent variable, which means even the derivative of x is no longer 1, but rather dx dt. So let's differentiate. 4x, 4 dx dt. 3y to the power of 4, remember. Y to the power of n, if you want to differentiate, you get n y to the power of n minus 1 y prime, or n y to the power of n minus 1. dy dx, in this case, dy dt. So 3 times 4, 12y cubed, dy dt. X squared, 2x dx dt. Just plug in. Four times dx dt is 10, plus 12 times y is negative 2 cubed, dy dt missing. 2 times 4 times 10. 4 times 10, 40. 2 times 4, 8 times 10, 80. Negative 2 cubed, negative 8 times 12, negative 96. So that's what we have. Subtract 40 from both sides. Negative 96 dy dt is 40. Divide by negative 96. And they are both divisible by 8. We get minus 5 over 12. That is the final answer, everybody. However, if they wanted us to solve for dy dt first and then plug in, that means we should move this to the right, becomes negative. And on the right side, we can see the common factor of 2 dx dt, and then we get x minus 2 divided by 12y cubed. Drop the common factor of 2. dy dt is dx dt times x minus 2 over 6y cubed. Now, if you plug in, you get exactly the same answer. Find dx dt for the equation 3x plus y e to the power of x equals 20, where dy dt is negative 8, x is 0, y is negative 1. Again, the independent variable is t. So this gives us 3 dx dt. This one is the product of y and e to the power of x. We put a raised dot in between, and we say, okay, it's f times g. We are going to use the product rule, f prime g plus g prime f. So y, the derivative is dy dt times g e to the power of x, g prime e to the power of x times dx dt, because remember t is the independent variable. So g prime e to the power of x dx dt times f, which is y. And the right side is a number. Any number results in 0. And believe it or not, let me box this. This is it. As far as the calculus goes, the rest is elementary algebra, everybody. Let's plug in. So 3 times dx dt minus 8 e to the power of 0 plus e to the power of 0 dx dt times negative 1 times 0. And equals 0, and I'm going to say, okay, this is 1, so is this one. 3 dx dt and negative dx dt, they add up to 2 dx dt. Minus 8 moves, becomes positive 8. Divide by 2, and therefore dx dt is 8 halves, or simply 4. If we were to solve for dx dt, then we would move this to the right and make it negative. These two, they have a dx dt in common, so we get 3 plus y e to the power of x times dx dt on the left side. The right side doesn't change. And you divide the right side by the parentheses, and you're done. If you plug in those numbers in, you get exactly the same answer as we did here, everybody. Find dy dt, again, t is the independent variable, for the equation 5x plus y to the power 4 minus x equals 6, where dx dt is 3, x is 2, y is negative 9. All right, we are going to differentiate, and looking at this, we are going to go with the extended power rule. 4 times the same thing to the power of 3, so 5x plus y to the power of 3. And then the chain rule applies. The derivative of the parentheses is 5 dx dt plus dy dt. We're done with this now. Minus x becomes minus dx dt, equals 6 becomes equals 0, because any number, when you differentiate, you get 0. Now we're going to plug in, which means we're going to replace the x with 2, y with negative 9, dx dt with 3. So just plug in. So 5 times 2, 10. Minus 9 is 1. This is 1. Cube it doesn't make any difference. It's still 1. This is 15. Distribute. 4 times 15 is 60. 4 dy dt minus 3. 60 and negative 3, they give us 57. 57 moves, becomes negative. Divide by 4. dy dt becomes negative 57 over 4. This is the final answer. I'm not going to solve for dy dt. I'm going to leave it for you in case come up with the answer. Falling sand is forming a cone-shaped pile. Okay, you have to draw the setting. So the question is, what is a cone shape? You should know this is the shape. This is the radius of the base. This is the height. The volume of the cone is increasing at the rate of 54 pi cubic inches per minute. What is the volume of a cone? You should know it's 1/3 pi r squared h. So you should have the drawing. You should know what is r, what is h. Then you can move on. Without this, we can't. The height of the cone is twice the radius of the base. The height is twice the radius of the base. Find the rate at which the radius changes when the radius is 6 inches. So we are going to write everything that is given symbolically. First and foremost, we should know this formula. Again, we draw this, we write this formula. And now, what is this? The volume is increasing at this rate. This is dV dt, 54 pi cubic inches per minute. Height, h, 2 times r. H, 2 times r. What are we looking for? dr dt. At what point? When the radius is 6 inches. So this explains everything that is given symbolically. A quick recap. We should know this shape. We should know this formula. We're going to write the formula. V is 1/3 power squared h. dV dt is given as 54 pi cubic inches per minute. The height is 2 times the radius. They said so. dr dt is missing when r is 6 inches. So bear in mind, the volume is the function of r and h, and we want to find dr dt. Because h is 2r, we're going to replace it. Otherwise, you have to use the product rule, and you don't get to finish the job anyways. But because we want dr dt, h is replaced. If we wanted dh dt, then r would be replaced. So let's do so. And so this becomes 2/3 pi r cubed. To differentiate this, we're going to write dV dt is 2/3 pi, because 2/3 pi is just a coefficient, a number, a multiplier. And then r cubed differentiated, 3r squared dr dt. Two pi r squared dr dt. We can plug in, or we can solve for dr dt, makes no difference. We are going to replace dV dt with 54 pi, 2 pi, or we replace it with 6, dr dt will be found. Now, obviously, this is 36 times 2 is 72, so we have 72 pi. We're going to divide both sides by 72 pi. The pi's from the top and the bottom cancel out. 54 and 72 divisible by 18, we get 3/4 units of the radius, change in r, over units of the time, change in t. So 3/4 of an inch per minute. Therefore, we're going to write the radius of the cone-shaped sand formation is increasing. Why is it increasing? Because it's positive. At what rate? At the rate of 3/4 of an inch per minute. A 20-foot ladder leans against the building. The base of the ladder slips away at the rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. Okay. Now, you have to draw the setting. I can't emphasize this enough, everybody. If you don't have the drawing, I have no idea how you come up with the answer. Not only you have to do the drawing, then you have to define your variable. So here's how it starts. Looks like this, that the ladder is here. This is the ground. This is the wall or the building. And it's moving this way. Therefore, it's coming down this way. So we have to define our variables first. So we're going to say, okay, the base is x, the height is y, and the ladder is fixed at 20 feet. So that's what we begin with. As it moves this way, it creates the speed dx dt, it slips away. Creates the speed dx dt is 2 feet per minute. As it moves this way, it comes down this way, creates the speed dy dt that we don't have, we don't know, and we want to find. So we're going to write, given dx dt equals 2 feet per minute, find dy dt when the base, what is the base? X. This is what I mean by defining your variable, is 12 feet. So drawing, defining variables. So having said that, what other thing do we know? Pythagorean theorem indicates a squared plus b squared equals c squared. Therefore, let's write it here. Let's actually erase it. A squared plus b squared equals c squared. That means x squared plus y squared is 20 squared. So that's a piece of information from geometry we should have. Now we are going to differentiate both sides with respect to t. 2x dx dt plus 2y dy dt. This is a number, 400, results in 0. We almost have everything. At x equals 12, what is y? We plug it in to Pythagorean theorem, and we say x squared, which is 12 squared, plus y squared, which is missing at that point, equals 20 squared. 20 squared is 400, 12 squared is 144. We're going to move the 144 and subtract it from 400. 256, and y becomes 16 feet. We are ready to plug in. Therefore, we are going to write 2 times x, which is 12 feet, times dx dt, which is 2 feet per minute, plus 2 times y, which we found it to be 16, times dy dt, which is missing. That's equal to 0. 2 times 12 times 2, 48. 2 times 16, 32. Move the 48, make a negative. Divide by 32. Both numbers are divisible by 16. Negative 3 halves, units of y over units of time. Negative 3 halves, feet per minute. Obviously, x is increasing, the x dt must be positive, y is decreasing, dy dt must be negative, and we write the height of the ladder is decreasing at the rate of what? 3 halves feet per minute. Do we write negative here? Absolutely not. When we mention decreasing, that takes care of the negative sign, okay? Now, when this change occurs, class, as this moves this way, also this angle, as well as this angle, both of them change. This is the angle between the ladder and the ground. This will change. This is the angle between the ladder and the wall or the building. That will also change. So let's look at that question now. We are repeating the question. A 20-foot ladder leans against the building. The base of the ladder slips away at the rate of 2 feet per minute. Find the rate of change of the angle between the ladder and the ground when the base is 12 feet from the building. Again, we are basically looking at the same question, but slightly different. So let's do the setup. So here's what we have. A ladder leans against a building or a wall. It moves this way. Okay. And so we are going to define our variables. This is x, the base. The height is y. The ladder, 20 feet. As it moves this way, it creates the speed. dx dt equals 2 feet per minute. As it moves down, of course, we've already discussed dy dt, but more importantly, this one changes and it creates d theta dt, and that's what we want to find. That is understanding the question and defining variables. So let's write When dx dt is equal to 2 feet per minute, we want to find d theta dt at the very moment when x is 12 feet. So that is the explanation of the situation. So remember, in related rates, we want to relate variables and quantities we know versus what we are looking for. So we know x. We happen to know y from the previous one, but in any event. And we are interested in d theta dt, so we have to find the relationship between theta and x and y. And so notice, if you look at this angle theta, cosine is the adjacent over the hypotenuse, whereas sine is the opposite over the hypotenuse. So cosine is x over 20, and sine is y over 20. So that's, again, we are looking at information from basic trigonometry. Now, we can use any of them you want. We also have y from the previous page, but always use what's given. X is given, so use this one. Why is that? Maybe we made a mistake when we calculated y, so don't take a chance. Always use the given. Having said that, we are going to deal with this. We are going to differentiate this, and to do so, I'm going to say cosine theta, the derivative is negative sine theta. Theta, it depends on t, so times d theta dt, and I'm going to write this as 1 over 20 times x, just because I want everybody to see we have 1 over 20 times dx dt. Okay. You don't have to rewrite it like that. I just want to make sure that it makes sense. So having said that, we have minus sine theta. What is sine theta? Y over 20. Okay. Now, we've already calculated the y from the previous page. I'm going to remind you that we used Pythagorean theorem, x squared plus y squared equals 20 squared, 12 squared plus y squared equals 20 squared, and we ended up with y being 16. Therefore, I'm going to replace the y with the number we found, 60. Now, at this point, I hope you see that I can drop the 20 from both sides. So we have negative 16 d theta dt equals 2. This is just 2. So divide both sides by negative 16. Minus 16 d theta equals positive 2. Divide by negative 16. D theta dt becomes negative 1 over 8. Units of theta is in radians over units of time, radians per minute. The units of any angle in calculus is always is in radians unless otherwise mentioned, everybody. What does it mean? The angle between the ladder and the ground theta is decreasing. Why is it decreasing? Because this is negative. At what rate? At the rate of 1/8 of a radian per minute. Why aren't we writing negative here? Because decreasing will take care of the sign. Okay. Example number 8, a spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius changing? Again, reminding you of what we did in the very beginning. Here's a spherical shape with the volume of 4/3 pi r cubed, we should know. So the volume is 4/3 pi r cubed, and it's deflating. That means dv dt is minus 8 cubic centimeters per minute. How fast is the radius changing? That means we want dr dt at what point when the radius r equals 20 centimeters. So this is the translation of the question into mathematical symbol. So having said that, let's start with this and differentiate. So we want dv dt, and it starts with 4/3 pi because that is just a multiplier. There's not much we can do. R cubed with 3r squared dr dt. So we get 4 pi r squared dr dt. We can solve for dr dt or just plug in right here. That means replace the dv dt with -8. 4 pi times replace the r with 20, so 20 squared. 20 squared, 400 times 4, 1600 pi. 1600 pi. We're going to divide both sides by 1600 pi. And therefore, 16 becomes 2, -8 becomes -1, and we get -1 over 200 pi, units of r over units of t, centimeters per minute. Roughly, again, this is exact answer. Let's just write it again. Exact. Now, an estimate with a bunch of decimals. How many? Whatever they ask you. -0.001592 centimeters per minute. What does it mean? The radius is decreasing. Why is it decreasing? Negative. At what rate? At this rate, 1 over 200 pi centimeters per minute. And again, when we mention decreasing, we don't have to write the negative anymore. So that's it, everybody.